welcome back guys to the third video of my channel Subject-o-Phile. Today we are not going to discuss any kind of question, rather we are going to discuss a concept of chemistry which is very important because I'm going to start today with organic chemistry, and people generally say that you have to remember reactions, but let me tell you that there is nothing to remember reactions in organic chemistry. Rather, everything is logical, and the very basics is you can predict the product of any kind of organic reactions if you have the basic idea of the reaction mechanisms. So we are going to study today one of the very important reaction mechanisms of the entire 11th and 12th syllabus, that is the Cannizaro reaction from the carbonyl compounds, or you can say from the aldehyde chapter. So before beginning with that, let me tell so brief you about what is actually Cannizaro reaction. Basic definition. Okay, the aldehydes which have no alpha hydrogen undergoes a redox reaction in presence of a strong concentrated base which is 50% in concentration of OH minus, where 1 mole aldehyde will oxidize to salt of carboxylic acid and another mole of aldehyde will reduce to the corresponding alcohol. So what does that mean? We will understand it by a chemical reaction equation. Okay, now uh, here, since there is absence of alpha hydrogen, so there is no chance of formation of a enolate or nucleophile via tautomerism, and hence this is the least favorable both thermodynamically and kinetically, least favorable reaction of carbonyl compounds in comparison to haloform or aldol condensation reactions. You know that in both haloform and aldol condensation reactions there is a presence of alpha hydrogen, for which the base can first abstract the hydrogen to create a carbanion, which and basically via tautomerism we can choose the most thermodynamically stable enolate, and that will participate in the reaction and will act as a nucleophile for the condensation reaction. But here there is no alpha hydrogen, for which this is the most narrow path and the least favorable path of reaction for any kind of carbonyl compound, and that is why it is only possible for only those carbonyl compounds which does not have an alpha hydrogen. For example, we take an aldehyde which is formaldehyde having no alpha hydrogen. So if we take two species of formaldehyde, 2 moles and 2 moles of formaldehyde, then it will undergo self reaction in presence of 50% OH minus to give uh, formic acid, the sodium salt of formic acid, plus an alcohol which is methanol in this case. So how this reaction happened, for that we need to understand the reaction mechanism, the very important part, so that you can do any kind of you can predict the products of any kind of Cannizaro reaction by just basic idea. Okay, the first step is, there is the OH minus in the basic in the entire medium, which acts as a nucleophile and attacks the carbonyl center here, which opens the C double bond O, and it forms by rapid equilibrium step. It forms this species right here. Okay, you can easily understand that. So if we have to write the uh, expression for the equilibrium constant, it would be simply this compound by this times this, the basic idea of equilibrium constant, and by getting the suitable expression for this concentration of this species, we can easily write in terms of K equilibrium and the concentration of formaldehyde and OH minus. Alright. Now, K equilibrium, we easily know K equilibrium depends on nature of aldehyde taken, because see, this is a nucleophilic addition attack, right? So this attack will be more faster if this carbonyl center is more reactive or it is more electrophilic, because this is a delta positive center, right? This is a delta positive center, and this center will be more reactive if the electrons from this C sigma CH bond or sigma CR bond is more towards this side, right? Is more pulled towards this side. So the carbonyl center will become more delta positive, and this will increase its reactivity, and thus the rate of the reaction or K equilibrium will also increase, right? So definitely that happens. So in terms of reactivity and of the carbonyl carbon and the steric factor, so definitely K equilibrium for HCHO will be greater than K equilibrium for PHCHO, because pH or phenyl is a donating has a donating effect, right? It has excess electrons, so it has a donating effect from the aromatic ring. This creates, or this reduces the reactivity of this carbonyl center, so the K equilibrium also decreases. Now, the second step, which is the very most important step because it is the rate determining step of this reaction. So what happens is the species that is already formed in from the first step. Now, the O minus which is formed here is not that stable, as it comes back, reverses back to form C double bond O, which is very stable thermodynamically, and this hydride simultaneously breaks away. Now this hydride, actually what happens is, this hydride does not independently break away because the lifetime of a hydride ion is very small. So what happens is this sigma ch bond directly or simultaneously attacks this carbonyl center of the another formaldehyde molecule that we have taken. So this reaction has a rate constant of K2, which is the rate determining step, and after this attack we get formic acid and a CH3O minus ion, but due to intermolecular proton transfer, this CH3O minus takes the hydrogen from here, and this results in a salt of formic acid and a alcohol. Alright, that is CH3OH. Now if we write the rate of this reaction, this will be K2 times the product of, because it's an elementary step, right? The product of the reactants that we have taken. So we can replace, we know this species we have already got from the first step. We can replace this expression in that equation to get the final equation of rate, which is, and the rate constant is definitely K2 into K equilibrium. This is the final rate constant, and the order is 2 plus 1, so it is 3. So order is 3. Now H minus never, as I told, H minus never acts as a nucleophile, as its lifetime is too short to be called as a nucleophile. Hence H minus always acts as a base. Very important concept, a very important concept. H minus always acts as a base. Now, since attack of H minus, which acts as a base after leaving CH bond, is a continuous and simultaneous process, so it appears that H minus acts as a nucleophile. But here, H minus cannot be isolated from the reaction medium at any time. That is why we concluded that it is not a nucleophile, because any nucleophile which is said as a nucleophile has a definite lifetime, or it can be isolated. So this attack is actually the attack of sigma CH molecular orbital of HOCH2O minus at the pi antibonding MO of the, like, C double bond O MO of HCHO. This is why intramolecular Cannizaro is always faster than intermolecular, because since in intramolecular you don't have to have the reaction between two different molecules, rather the reaction occurs within the same molecule, and the proximity of the attack is very close. That is why the reaction occurs at a faster rate. Now, if now there is two, like, statements or conclusion from this. If K equilibrium controls the reaction, the more reactive carbonyl carbon should be oxidized as it forms the intermediate. As we have already seen, K equilibrium is greater for more reactive carbonyl centers. But if K2 controls the reaction, the less reactive carbonyl carbon should be oxidized, as it is a better hydride donor. Greater electron density on the carbonyl carbon. Now, there is a very important thing. See, if the electron, as I said, the reactivity depends on the delta positive, right? But if somebody donates the electron here, this reduces the delta positive character of the carbonyl center, but this greater electron density in the carbonyl center helps the hydride leave easily, because this bond then becomes weaker. CH bond becomes weaker, and the energy of the sigma CH orbital actually increases, which leads to a very faster attack to the pi antibonding orbital of the sigma CO bond. So of the pi antibonding of the C double bond O, sorry, the pi antibonding of C, the attack is very faster at that case, in that case. So what happens is, uh, greater electron density on carbonyl carbon will result in more easier cleavage of CH bond, and thus tendency of hydride donation will increase, as I said. So uh, what there is two contradiction. If K equilibrium would have controlled the reaction, then the more reactive, which is the more delta positive carbonyl center, would have been uh, it should have been oxidized. But if K2 controls the reaction, then the less reactive carbonyl carbon should be oxidized. So which is true? Why this contradiction arises? Now let me first tell you the answer which is true. Okay, because in Cannizaro reaction, the more reactive carbonyl carbon always oxidizes, which means it is a K equilibrium control reaction. Now why it is so? Why it is so? So the second step is a rate controlling step, but what K equilibrium decides, so the equilibrium constant from the first step decides which carbonyl carbon has to be oxidized in this reaction. See, concentration of OH minus is taken to restrict leaving of OH minus as in the solution, as it is already present in the solution. So this OH minus, obviously the tendency when this minus comes back down here, it reverses, the step reverses. The first tendency, leaving tendency is of this OH minus, because it is a much more it is a better living group than a hydride, right? Hydride is a very poor living group. OH minus is a great living group. So when it reverses back, the natural tendency should be the leaving of this group, right? But why it does not happen here? Because the excess of OH minus present, which is in the solution, actually does not let to the increase of more OH minus in the solution. So this path is blocked. That is why the only chance left is the leaving of the hydride here. So reversibility of this reaction is restricted, as I said, and the forward shift of the equilibrium occurs, resulting in leaving of hydride. Okay, so now see, R increases. As I said, electron density, more electron density is increased, the more good is the tendency of the leaving of hydride group. So the rate for uh, the R group will be aryl, which will be the most because it has the most electron density for donation. Then 3 degree carbon, 2 degree carbon, then 1 degree, then hydride. Obviously. So now, if concentration of OH minus is increased, then the hydrogen is abstracted and other O minus comes to existent. Now, what does this mean? Okay, so if the concentration of this OH minus is more and more increased, like it's taking very much excess amount, then what happens? This is as this is a base, this comes and obstructs this hydrogen. It has a tendency to obstruct this hydrogen, and thus it becomes O minus here. Here also O minus. Now this O minus is a very good donor, right? You all know O minus is a very good donor. And when it reverses back, it actually what happens? It increases the electron density in the carbon, right? It increases the because here it is very delta positive, but when it reverses back, it actually decreases this delta positive character because it is donating a pair of electrons here, right? So this electron density on this carbon increases very much, which results in a very faster leaving of the hydride group. So this 2O minus formation actually increases the rate of the reaction very much because hydride group is much easier to leave in this case. So there are two O minus donor. This increases density of carbon highly, which results in higher rate of leaving of hydride. Automatically, K2 of the reaction also increases. So inductive effect of R is negligible with respect to O minus donor. Obviously, O minus donor is a resonance donor, right? So the inductive effect in front of resonance effect is negligible. You all know that. So this reaction rate is controlled by K equilibrium and not K2. More reactive carbonyl carbon always oxidizes here. So the when we are studying about which reaction should occur first, you should always know that the more reactive carbonyl carbon will always oxidize and not the least reactive carbonyl carbon. So this is a K equilibrium control reaction. Now since the one for this abstraction of hydrogen, one extra mole of OH minus is required when it is taken in a very excess amount. So in this case the order of the reaction becomes 4. Okay. There are some questions for this Cannizaro reaction, but we will discuss these questions in the next video. Apart from before that, please go through this video once again to understand the concept of Cannizaro reaction mechanism very nicely because this is a very important reaction and I think one of the most trickiest reaction in terms of reaction mechanism. So only after you have understood this concept very nicely, then only you can go and attempt these questions. So before attempting these questions, I hope you all will go through this video once again, and you will make your notes nicely. Till then, thank you for watching this video. If you have liked the video, please share and subscribe my channel, so that the other people might get the benefit of these videos, and they can prepare for their exams very nicely. So thank you and goodbye. Meet you in the next video.